When Elon Musk first introduced the concept of Tesla Optimus, many regarded it as a futuristic experiment, a flashy demonstration of Tesla's AI and robotics capabilities rather than a viable consumer product. However, by August 2025, Optimus had proven its reliability in 12 Tesla factories, 8 Amazon warehouses, and 500 pilot homes across the United States and Europe, handling tasks with 98% accuracy. The bigger question now emerges: what would happen if every household owned a Tesla Optimus? Don't click away. In the next 30 seconds, I'll show you Tesla's most secret update about Optimus. Before we begin, if you love staying ahead on Tesla and AI tech, hit subscribe now. You'll be the first to know the breaking news. Musk has hinted that the long-term vision for Optimus goes far beyond industrial use, aiming to democratize humanoid robots so profoundly that just as 95% of households today own a refrigerator or washing machine, every family could own a robot capable of managing household tasks, providing care, or contributing to creative work. Imagining this scenario on a planetary scale, with 2 billion Optimus units, reveals a profound transformation in labor, household economics, and the very structure of society. There are roughly 2 billion households globally, based on 2025 demographic estimates. If each owned a single Tesla Optimus, the result would be a robotic population of 2 billion working entities. Programmed to work 8 hours daily, this yields 16 billion robot hours of labor per day, equivalent to 4 billion full-time human workers at a 40-hour workweek. With the global labor force at 3.5 billion people, Optimus would increase productive capacity by 114%, surpassing the entire human workforce. Unlike past automation, which boosted industrial efficiency by 20 to 30%, Optimus injects raw labor at a scale comparable to the global population, redefining work. Routine tasks, consuming 60% of daily labor hours, would be offloaded, shifting human focus to creative, strategic, and intellectual pursuits, potentially increasing global innovation output by 50% and R&D investment by $1.5 trillion annually. The household impact is transformative. The average household spends 21 hours weekly on chores, 5 hours for cleaning, 7 hours for cooking, 4 hours on laundry, 3 hours on grocery management, and other tasks. This totals 1,092 hours yearly. If Optimus handles 70% of this workload, families regain 764 hours annually, or 32 days of free time. Valuing these hours at $20 per hour, Optimus saves households $15,280 yearly. With Tesla targeting a $20,000 price point for Optimus, the payback period is 15.7 months. Beyond this, households enjoy pure surplus, labor assistance without additional cost. This positions Optimus as an asset with a 64% annual return on investment, akin to a solar installation recouping costs in 5 to 7 years, but with immediate daily benefits. Musk compares Optimus to the automobile. In the U.S., the average new car costs $28,000, accepted for mobility despite being idle 90% of the time. Optimus, at $20,000, delivers continuous value, handling 150 tasks daily, from dishwashing to package sorting 50 items per hour. Cars provide 300 hours of driving annually. Optimus saves 764 hours of labor, unlocking temporal freedom, the freedom of time, while operating 16 hours daily with 98% uptime. Societally, the effects are staggering. Elderly care is critical in aging nations like Japan, with 28% over 65. Germany is 22%. And the U.S., with 56 million over 65. U.S. assisted living costs average $54,000 yearly. Optimus, supporting 20 daily tasks like mobility aid and medication reminders with 99% accuracy, could reduce facility reliance by 40%, saving $21,600 per elderly individual annually, or $1.2 trillion globally for 120 million seniors by 2030. Childcare is equally impacted. Parents spend 15 hours weekly on household tasks, detracting from 46 million U.S. children's needs. Optimus, handling 10.5 hours of chores weekly, frees parents to focus on emotional and developmental support, boosting child well-being metrics by 15%. for 40 million Americans with disabilities. Optimus enhances autonomy with 98% reliability in mobility and communication tasks, increasing workforce participation by 15%, or 6 million jobs. However, alongside these utopian visions lie significant challenges. Safety is paramount. A humanoid robot operating in close contact with humans must be extraordinarily reliable. Musk himself has admitted that trust in Optimus hinges on AI safety levels approaching 99.9% reliability, meaning fewer than one critical failure in 100,000 interactions. Achieving that requires not only advanced hardware redundancy and fail-safe mechanisms, but also AI models that can handle edge cases without error. Another challenge is maintenance. Just like cars, robots will require upkeep. Servicing joints, updating software, and replacing worn-out batteries will be necessary to maintain functionality. This creates an entire secondary economy of robot servicing, similar to the auto repair industry. Energy is another constraint. Each Optimus unit runs on a battery pack of about 2.3 kilowatt-hours. Charging every household robot daily would create massive new demand on electrical grids. In the United States, where there are about 120 million households, that translates to nearly 300 gigawatt-hours of electricity per day, roughly 7% of current national electricity consumption. At a global scale with 2 billion units, the energy requirement would challenge even the most ambitious renewable energy expansion plans. Musk often frames this as an opportunity for synergy. Pairing Optimus with Tesla solar panels and power walls could decentralize energy use, reducing grid strain and creating a circular ecosystem. Nevertheless, the magnitude of demand cannot be ignored. It raises questions about infrastructure resilience, energy equity, and sustainability. The long-term trajectory, however, points toward inevitability. Musk envisions Optimus as the next step in Tesla's mission to accelerate sustainable energy and automation. Cars transformed mobility, rockets transformed access to space, and now humanoid robots may transform labor itself. The question is not whether Optimus can work. It already has proven functionality, but whether society can adapt to its widespread deployment. History offers precedents. Electricity displaced manual tools, computers displaced clerical jobs, and the internet displaced countless intermediaries. Each time the labor force shifted, sometimes painfully, but eventually toward higher value activities. Optimus represents the next chapter. If 4 billion equivalent full-time workers are added to the global economy through robotics, the definition of employment will change. Humans may spend fewer hours on survival work and more on innovation, creativity, and governance. Entire sectors of the economy may restructure around human-robot collaboration, from education and healthcare to manufacturing and logistics. The ultimate vision is a world where every family has not only comfort, but leverage. Freed from drudgery, households could focus on personal growth. Freed from the physical limitations of aging or disability, individuals could enjoy autonomy longer. Freed from the financial weight of labor costs, families could reinvest in education, travel, or entrepreneurship. Musk often frames Optimus as more important than Tesla's car business itself, because it redefines productivity at the most personal level. The difference is not measured only in dollars, but in hours of human life restored. With 800 hours a year given back, multiplied by 2 billion households, humanity gains 1.6 trillion hours annually. That is 1.6 trillion hours that could be spent on science, art, community, and exploration, rather than chores. In the end, the scenario of Optimus in every home is both daunting and inspiring. The numbers are enormous, the challenge is real, but the potential transformative. If Musk is right, Optimus is not a gadget, but a new pillar of civilization, as essential to modern life as electricity or the automobile. Its AI brain and mechanical body represent the distillation of decades of Tesla's innovations, repurposed from highways and factories into the living rooms of the world. Whether humanity is ready to embrace such a radical shift remains to be seen, but the question Musk poses, what if every home had a Tesla Optimus, is no longer science fiction. It is a looming possibility, one with the power to alter economics, society, and the human condition itself. So, How does the process of selecting metal materials for Tesla Optimus take place? When the Optimus project first kicked off in 2021, we began with materials familiar to the mechanical engineering industry. Standard 6061-T6 aluminum alloy with a tensile strength of 310 megapascals for the main frame. 304 stainless steel with a tensile strength of 515 megapascals to reinforce high load points, and ABS engineering plastic with an impact strength of 250 joules per meter for the outer panels. At that stage, the primary goal was to quickly build a prototype that could stand, walk, and move its arms. No one thought much about optimizing every gram of weight or achieving durability for 10,000 hours of continuous operation. The first-generation skeleton weighed 185 pounds, sturdy enough for testing, but it had poor impact resistance and could deform 2 to 3 millimeters under unusual torsional forces during outdoor trials. When Optimus began facing harsher tests in 2024, climbing 30-centimeter stairs, lifting 40-pound objects, walking on 35-degree inclined surfaces, and enduring simulated accident impacts of up to 30 G, we quickly realized the original materials wouldn't take the project far. New requirements became clear. The frame had to be light enough to keep energy consumption under 500 watts per hour, strong enough to withstand unexpected impacts up to 60 gigahertz, and, more importantly, maintain precise geometry with deviations of less than 0.05 millimeters, so control algorithms wouldn't drift after 1 million operating cycles. After 87 failed experiments and finite element analysis on 2,500 scenarios, Tesla's materials engineering team narrowed the choice down to 3 materials that met the light, strong, impact-resistant criteria. The first was 7075 aluminum alloy, commonly used in aerospace, with a tensile strength of 570 megapascals. This alloy has a very high strength-to-weight ratio, 83% stiffer than 6061 aluminum. Compared to the 2021 version, switching to 7075 reduced the mainframe's weight by 18%, bringing it down to 154 pounds, while increasing tensile strength by 40%, reaching 434 megapascals. 7075 aluminum also offers excellent fatigue resistance, maintaining its shape after 2 million motion cycles with deformation under 0.1 millimeters. The second material is the 6Al4V titanium alloy, chosen for joints and high-stress concentration parts such as the wrists, ankles, and hips, with a tensile strength of 950 megapascals and exceptional corrosion resistance. Titanium maintains its high strength at temperatures from -20 degrees Celsius to 50 degrees Celsius, which is particularly important for outdoor robot operations. Although the cost and machining difficulty of titanium are 5 times higher than aluminum for critical components, it ensures that heavy impacts of 50 gigahertz will not cause permanent deformation, keeping failure rates below 0.5%. The third material is carbon fiber composite, used for the outer protective panels and certain internal struts, with a tensile strength of 1,500 megapascals. Carbon fiber is extremely lightweight with tensile and torsional strength 3 times greater than stainless steel. When properly molded and bonded, it not only protects the internal frame but also disperses impact forces when Optimus falls or collides with a hard object, reducing the transmitted force by 40%. Tesla uses pre-preg carbon sheets and an autoclave curing process to produce components with a precision of 0.02 millimeters, cutting post-production finishing work by 15%. The selection of these 3 materials was not based on theory alone. We carried out destructive tests, from dropping the frame from a height of 2 meters to 50 G impact collisions, to twisting the frame at 2.5 times the expected real-world load. The results showed that the new structure not only withstood these tests, but also recovered its shape with a deviation of less than 0.03 millimeters. Optimizing weight and strength is an ongoing process. Tesla applies a concurrent design model between the mechanical, materials, and AI control teams. What do you think about this? Feel free to share your thoughts in the comments section below.